Greetings, Ohio Valley. This is Dan Lima with OSU Extension from Belmont County.
And this is Karen Cox from WVU Extension in Ohio County. Thanks for tuning in to Extension Calling, your source for research-based information for the farm, garden, and home. COVID-19 vaccines were given to tens of thousands of people in early clinical trials and to hundreds of millions of Americans since. Top health experts agree that COVID-19 vaccines are safe, effective, and trusted. Visit vaccinate.wv.gov or contact your local health department. All right, so it is that lovely time of year that nobody looks forward to, which is the time where we have to set our clocks back and enjoy some more darkness.
Yeah, no, we get to go out early in the morning when the sun's up and then come back when it's dark. So it's a trade-off. Most people, I think, would prefer to have a little bit of light later than earlier, but because we take our clocks back, right? So
yeah, we fall back.
So it'll be dark when we get home from work.
But also, the days are getting shorter in general. So not only are we getting home in the darkness, pretty soon we'll be getting up in the darkness too, just because the days are shrinking in length. And that affects plants as well as people.
I was about to say, yeah, the plants aren't going to get confused because they don't worry about that kind of stuff.
But they do pay very close attention.
They worry about the sun. No, yeah, I mean, I'm at the time.
No, they don't care about the time.
The time screws me up. The sun, the day's getting shorter, that just happens, and you just acclimate and get used to it. But yeah, so the plants are just used to responding to the light. But these clocks, I tell you what, I don't think we were designed for them, and neither were plants.
Yeah. When I was working in forestry, I actually got to get up with the sun, and that actually worked for me. I got up really early in the morning, but I was on the same clock as the earth was, and it was awesome because I felt like I was in tune and I didn't have some weird alarm blaring in my head forcing me out of bed in the morning. I'm not a morning person, in case anyone out there hasn't picked up on that.
Yeah, and that sunlight's so important because that is what actually entrains our clock to function the way that we were designed to function as far as being a nocturnal or the diurnal animal.
Right.
So, all animals, there might be an exception, probably like things deep in the ocean. But just about everything responds to light.
Mm-hmm.
And plants, because they're so light dependent, with a few exceptions, of course, right? So what makes a plant is having a plastid. It doesn't necessarily have to have a chloroplast. So there are completely parasitic plants where they have the remnants of the machinery to photosynthesize, but they're still a plant because they have a plastid. So I'm sure, it's one of those things like there's got to be a response to light somewhere in there, but it's not necessarily photosynthesis. And I was actually going down deep underwater in those vents, right? But I'm thinking more that's algae and bacteria.
Yeah.
That kind of make their energy through those sulfur vents deep in the ocean where there's no light.
That's some crazy biology right there. I would love to have a specialist come in and talk to us about that just because I'm fascinated by it.
I think that's what's growing in my garden. That's the problem. No,
you probably got some mycetes going on your garden right now.
All right. Because daylight savings, we were going to talk about not the daylight savings portion of things, but how light affects plant growth and just plant responses in general.
Right. Yeah. The duration of light is part of what they respond to. So they respond to duration, intensity, and what was the third one?
Third one is quality, and that has to do with the energy spectrum. So
right, how potent the light is.
Right. So light is energy, right? And the different wavelengths of energy in a certain spectrum are what we see, a visible light spectrum. So you got blue light that's a little bit higher in energy than you have red light. And if you look at the straddling things on blue to red light, you have infrared above blue that's higher energy, right?
What do you mean straddling things?
Like on the other side of blue and red.
Ah, okay, like indigo, violet type of things.
Yeah, so above blue, I guess, is another way to say it. you have ultraviolet, right? And we know what ultraviolet does because it's high energy, can cause cancer. But then as you drop in energy, you go to blue, and then you get all the different colors till you get to red. And then once you lose some more energy, you get infrared, which is heat. So you have the visible spectrum in between ultraviolet and infrared.
That's cool.
Well, I guess as cool as wavelengths can be, right?
It's always been fascinating. You know, light we take for granted. It's always there. It's around us. We as humans just see light, but we actually see a lot of different lights. We just don't recognize it. When you look at a plant and the plant looks green, that's because that plant is reflecting the green light back at us. It just likes the red and the blue, and it hangs onto those, and it says, go away green. It does absorb some green, but most of the green, it just reflects back out. And so whenever we see colors around us, that is that color of light that's being reflected back and not absorbed by that item.
So what you're referring to, Karen, are leaf pigments. And there is a pigment in leaves that does absorb the green. So when we talk about chlorophyll, let's go back to chlorophyll. Chlorophyll absorbs blue light and red light, and it reflects the green like you were saying. But because the leaf is predominantly chlorophyll, there's a lot of green reflected. But there is a pigment that absorbs essentially just in the green. Like what color leaves are there other than green? And I'm not talking about like fall. I'm just talking about like peak summer leaf color.
Purple. Or reddish purple.
And that's called anthocyanins. You'll see that pigment in grapes. They say it's an antioxidant in wines, right? You know, it's actually a plant pigment for another layer of protection that will actually absorb that green. So when you have anthocyanin included in there, the green gets absorbed, but because anthocyanin doesn't absorb in the blue and red, the chlorophyll still are able to do their thing, even though the leaf isn't green.
And then there are the leaves that have white on them, and that is typically due to a virus that affects the creation of the chlorophyll in the leaf. So you get those variegated leaves, and some plants even look like ghost plants. They're just all white. And that is, like I said, typically caused by a virus.
Yeah.
It's a defect in the plant. It's decreasing its ability to absorb light. And so if you have a variegated plant that's not getting enough sunlight, a lot of times that variegation actually goes away. And so if you have one that you bought at the store that was really pretty, it was like super different, and now it's just all green, that's because it's not getting enough light.
That's absolutely true. So we've bred in these viruses into the plants just because they have this variegated look to them. So in ornamental plants, having, I guess, a virus built into the DNA of that plant isn't necessarily a bad thing because we like the way it looks. The problem comes when you have a close relative of a crop. So a lot of times what we'll do is we'll grow these things in separate greenhouses. Like you'll do your produce in one greenhouse and your ornamentals in another greenhouse, because if that virus jumps from an ornamental to a crop plant for produce, then you can have issues because of the usage. We like the way the variegation looks in one case, but it can really affect the production of another one. So when you're growing both the ornamentals and the produce in the same place, they have to be separated, usually through different greenhouses or fields, because that can really cause some problems in the produce department.
Yeah, a variegated lettuce would not be good because it's not going to be as nutritious. It's not going to grow as well. And if you have variegated leaves on your tomato plants, they may not get enough energy to produce nice, juicy, sweet tomatoes.
Yeah, we breed based on how we use that plant. And there's a difference between eating it and looking at it.
So there's another plant that really reacts surprisingly to light, but it reacts more to the photo period or the day length, or actually more accurately, it's the night length that it's reacting to. And it's one that we're starting to look for, get ready for, because, you know, November's here, so we got to start planning for Christmas, right? But that's poinsettias. So your poinsettias are going to react to that longer night length. So they're called short day plants. And those plants are going to go into flower in those longer night or darkness periods. So you have your short day plants, which should be called long night plants. You have your day neutral plants, and then you have your long day plants or your short night plants.
Yeah. And what you're saying, Karen, is something that was discovered much later because, we called them, think about it. We have a 24-hour day length, right? So when you have sunlight that's over 12 hours, you have a shorter night period. And we saw that certain plants didn't flower when they were exposed to that long day and short night. So we called them short day plants because we're naming it after the flowering, right? So if we had a short period of day and a long period of night, they would flower. And usually we're talking less than 12 hours. 12 hours is kind of the critical light length where you have the separation.
Right.
But if we take an 8-hour block of light and then we do a flash of light in between a 16-hour block of darkness, it'll be like it never saw that long night, just that long day.
Right.
So it is that darkness that really kicks in.
Uninterrupted darkness.
Thank you. Yeah. And the funny thing is, where I think people really are impacted by this phenomenon is in seed germination, right?
Yeah.
Remember, we were talking about the light quality and we were talking about the wavelengths, and then you have ultraviolet, which is higher energy, all the way down to infrared, which is lower energy, right? And in between that was visible light. Well, the longer the wavelength, the more likely it passes through the leaf and doesn't get absorbed by those pigments that we were talking about. We talked about chlorophyll, anthocyanins. But what happens a lot too is that far red infrared light will pass through the leaf and hit the ground. A lot of seeds will actually not germinate when exposed to that infrared / far red light. It's just another way to kind of talk about that sector of energy. And it's very interesting because when does that happen? It happens when there's a canopy above it, right? So once you pull up all those weeds, and now you're letting the higher quality light through because you don't have anything shading it, then all of a sudden, all those seeds down there that have probably been down there for, sometimes years, will just receive that pulse of high light, which they see as daytime almost, and they just activate and germinate. And then you have a whole bunch of new weeds after you just weeded. That's a phenomenon that every gardener's familiar with.
Right. And, it's part of nature's successional process. Plants are designed to protect the soil. And if the soil is exposed, it's not protected. And so therefore, the plants jump into action and start working to protect that soil. You see the same thing after a timber harvest. You'll see a lot of those underlying seed beds that have been there for, 100 years. And you remove the timber, and what comes back? Your fast-growing weeds.
Garlic mustards.
Don't get me started there. We're not talking invasives today, Dan. But no, it's just fascinating because those so-called weeds have a very important purpose, and that is to keep the soil from leaving. And so in your garden, what could you do to simulate or to block that light? So which light are we trying to block here?
So we're trying to block the blue and the red. So the stuff that drives photosynthesis, right?
Right. The far infrared was what was passing through the leaves, right?
Yes. So the leaf is absorbing the blues and the reds. Then the far red goes right through it. So imagine this. You have an open field, right? When you have open sunshine, uninterrupted light going through, you got the entire spectrum, okay?
Mm-hmm.
When you put a leaf in there, the leaf is absorbing the blue and the red, the blue all the way to the red. And then the far red, which is beyond the red, goes through the leaf, okay?
Right.
Think of it in ratios, right? So the seed is seeing a very high ratio of infrared light as opposed to red and blue light, and that'll deactivate it. But once you remove that leaf, now you have the entire spectrum coming through, and that blue and the red light will drive it to germinate. It'll activate the seed. So I think I know where you're going with this. When we weed and there's that seed bank there, what can we do to cover up that full quality light from coming through? Mulch.
Right.
So you put some mulch in there, and now you don't have any more red and blue light activating the seed.
Right. Right. Yes, you are. That is where I was going.
I figured that's where you were going, but I mean, it is confusing, and I am looking at a graph. Otherwise, it's kind of a hard concept to grasp.
Right. And my kids are, why do I need to know the powerhouse of the cell and all that? Knowing this helps us to better understand why we do some of the practices that we do. So we know that we don't want these seeds to germinate, and so we're covering the soil. And now you're knowing why we cover the soil. It's to prevent those wavelengths of light from getting to the soil to trigger that growth response.
Yeah, it's a really interesting phenomenon. Another thing with quality of light that we can kind of touch on are light bulbs, right? So there's typically two types of light sources. One is a fluorescent light bulb, and one is a incandescent light bulb. Now, those of you that have been around a while, myself included, we're familiar with remember the inefficient incandescent bulbs, right? What would they do? What would they do, Karen?
They make light and they make heat.
They get really, really hot because incandescent light bulbs are very rich in that red and far red. Remember how after red, as you lose energy, you actually go into heat and you get infrared. Those lights are very high in the red and then infrared. Well, funny thing is that red light is usually what stimulates a plant to go into a flowering type of environment. And there's always exceptions. So
There's always exceptions.
But like when you have a fluorescent light, the reason why it doesn't heat up is because it has a lot more blue light. It's more in the blue light spectrum and less in the red light spectrum. So a lot of people in greenhouses and hydroponics will use more of that blue light to keep things vegetative. So things like lettuce, things like spinach that you don't want to go to flowering, besides day length, the quality can impact it as well. But we do everything we can to kind of prevent that. But after a while, most plants will just naturally flower after a while. You can only hold that back for so long on certain plants. And I want to say that lettuce is one of those things where eventually it will flower, but you can actually delay that by the quality of light. So more in the blues, the cooler lights is what we call them, as opposed to the red lights.
Mm-hmm.
And then day length is critical. It's a very big trigger for lettuce as well. So lettuce being a long day plant, you want to have those shorter days to keep it vegetative.
Right. Yeah. So let's talk a little bit more about what kind of plants are your long day plants versus your short day plants. Because we're getting into winter, so we're going to have a shorter day and a longer night. So let's talk about a day length that's less than 12 hours. And blueberries are first thing in the spring. So when you think about crops that you're going to harvest early, those are typically plants that will flower during that short day period. Now, your long day plants, where you need to have a day length of more than 12 hours or a night of less than 12 hours, then you're starting to look at your radishes, your spinach, your turnips, your wheat, lentils, dill, clovers. Those are going to flower when you have a longer day period available to them. So like when you think about carrots are a long day plant. But we don't want carrots to flower, right? We just want that root, because once it starts to flower, your carrot's going to get bitter and woody, and you don't want that, right? So we typically will plant carrots early in the spring or later at the end of summer so that they don't experience that long day period. We have that shorter day period, the longer night, which makes it stay in its vegetative stage, which is the part that we want to eat.
Just like the lettuce.
Right.
And here's another thing that we haven't really touched on too much is that light intensity, right? So we talked about the quality, we talked about the day length, but there's also the intensity. We're talking about things like number of photons per whatever, right? So the intensity it would be the equivalent of low beams and high beams in a car. The interesting thing is plants will convert light energy to chemical energy, which is another way of saying sugars. So there's that conversion factor. If you have a lot of light coming through, the plant will do two things. One, a lot of light can damage a plant because you're just bombarding it with energy. So the leaf will actually get thinner under high light situations to let more energy pass through it but it'll also make less chlorophyll because the chlorophyll can get overwhelmed and you can have too much energy in the system. So in highlight situations, you have a thinner leaf and a less pigmented leaf. In low light situation where every photon is important and is basically necessary to keep that plant alive, you'll have a thicker leaf to let less things go through, and you'll have more pigments to help capture the little bit that's there. So you'll get a thicker leaf and a greener leaf. Now, if you're asking me how I like my lettuce, I would rather have a thicker, greener lettuce. And one of the ways to accomplish this is by not putting it under high light situations, but more in the lower light intensity. So light has all kinds of different ways of affecting plants. And the science out there, it's amazing some of the experiments I've found all this out.
Yeah, it is. And that's the cool thing I love about science is we think we know something, we experiment, and we say, oh, we were wrong. It's not length of day, it's length of night. And we learn and we build and we grow. And unfortunately, in the way news reports on science is news speaks of absolutes, this is how it is. But that's not the case in science. In science, we only disprove things. So we can only say, well, it's not that, and it's not that, and it's not that, because that's how the scientific method works. We're living, we're learning, we're growing, and sometimes we're wrong. And that's the whole point. Testing your theory over and over and over again until you learn something new from it.
Yeah, and there's always an exception too.
There's always exceptions. And that's the fun thing.
And you can't dwell on it, like the whole thing we talked about, the seed bank,
right,
with the far red light kind of making it inactive. And as soon as you pull up everything and you have the full spectrum of light back on it, it'll activate everything. There's going to be exceptions where, the plant's not sensitive to that. But
yeah, there's a lot of plants that don't need light to germinate.
That doesn't mean that we shouldn't ignore that principle, right? And here's another interesting thing. People think that plants need light to green, and that's probably 99% true. If a plant never sees light, if it germinates in the dark, like certain sprouts that we eat, right? They're dark germinated. They're not green. They're like that yellow color. But there are more primitive plants that don't have a light trigger on them that'll just stay green all the time. And one of those things is moss. Moss is actually a plant. It's very primitive. It doesn't flower, but moss will always be green, even if it's there in complete darkness. So moss is one of those more primitive plants. That's the exception to that rule, that if it germinates in the dark, it's not going to be green. It's just very interesting, very cool. The world of plants and just examining some of those exceptions are really interesting. We were talking about day lengths here. Ohio is kind of an interesting place. We are at 40 degrees latitude, which means that the equinoxes, or when the day lengths are 12 and 12, are going to be in late March to late September. And in between those dates, we're going to have longer days than nights. So the times of the year that Ohio is typically going to be longer nights than days, so shorter days, I guess is another way to say it, would be September to March. And then after that, from March to September, we're going to start at 12 and 12, and then the days are going to be longer than the nights. So ideally, if it wasn't so cold, we could grow these long day plants that we want to keep vegetative, like lettuce and stuff, in between September and March. But we do have the challenge of temperature there to battle. So that's why we have things like high tunnels. That's why we grow things indoors. And a lot of times, we can take the sun out of the equation completely and grow things with artificial lighting, so that, we control the day length, we control the temperature, and we control the intensity. We can also control the quality of light too. It's just amazing. The more you know about this stuff, the more you can perfect the perfect environment to get the best quality produce, which is what we strive for in agriculture. And it's something that we see a lot in the grocery store, right? When we see hydroponic tomato, nutrient balance to that tomato plant under ideal light conditions. And they look at everything that we talked about. It's just something to think about. Very interesting. And the science of agriculture has been impacting us basically as long as we've been cultivating things. So it's amazing to think how far we've come.
Okay, West Virginians, this next bit is for you because we need your help. Access to health services in West Virginia is critical. West Virginia often falls at the bottom of national health rankings related to overall health, including many chronic diseases. But we need you to make your voices heard, as well as the voice of your community, by telling us your health needs. A team of our colleagues from WVU are working to improve health in West Virginia. And so, 1 in 14 West Virginians will be selected to participate in the Mountain State Assessment of Trends in Community Health, or MATCH, survey, to gather important health information specific to West Virginians. To make sure the statistics are accurate, we need to have 250 participants from each county respond. So far, only 6 of our 55 counties have met that response rate. Why is this important? To improve the health of West Virginians, we need to hear from you. Your feedback will help the state and local communities better address your health needs, increase access to health resources, and better understand the reality of health in your community. Please, if you happen to be one of the West Virginians randomly selected to participate in the MATCH survey, I encourage you to take the time to share your health experiences. You can take the survey online, by mail, or even over the phone. You can learn more about the MATCH survey by visiting wvmatchsurvey.org. That's wvmatchsurvey.org. Or you can call 304-581-1928. That's 304-581-1928. We appreciate your time and help in making West Virginia a better place.
Thanks for listening to Extension Calling. This show is a collaboration between OSU Belmont County Extension Educator Dan Lima and WVU Ohio County Extension Agent Karen Cox. If you'd like a transcript of this show, contact us at the office. Also, let us know if you enjoy the show by ranking us on your podcast app.